Hello and welcome to the Navy STP Tech Talk for Swing. Swing is an integrated circuit technology based on a novel semiconductor device process that uses nitrogen polar gallium nitride on sapphire high electron mobility transistors. Swing enables cost efficient and high performance integration of a low noise amplifier, power amplifier, and transmit receive switch on a single chip for microwave and millimeter wave transceiver applications. Swing is developed by MaXentric Technologies and is funded by a Phase 2 SBIR contract with the Office of Naval Research. My name is Isabel Teliez, and I am a senior member of the technical staff here at MaXentric. In this 10-minute presentation, I will outline the Navy challenge that Swing is addressing, the key advantages of the Swing solution, and the operational improvements that Swing could lead to if successful. I will also describe the current status of the technology and the planned transition strategy beyond Phase 2. MaXentric Technologies is an advanced technology research, development, and service firm founded in 2003. We are an industry leader in radio frequency technology and high speed wireless communications devices. We have offices in Fort Lee, New Jersey, San Diego, California, and Boulder, Colorado that provide design and manufacturing services for military, industrial, and OEM markets. MaXentric is based entirely in the United States and has a proven track record of successful SBIR technology transitions. Our wide range of products include wireless systems such as digital phased arrays, reconfigurable radios for small UAV and radar, digital signal processing platforms such as digital beamforming and software defined radios, advanced circuits and transceiver systems such as envelope tracking power amplifiers and millimeter wave MMICs, and wireless low power biomedical systems such as contactless continuous use vital sign monitors. MaXentric Swing technology was conceived, proposed, and developed in response to STTR topic N 23A-T028. The objective of this topic is to maximize the performance of RF switches in nitrogen polar gallium nitride HEMTs based on an epitaxial layer structure capable of 4 millimeters power density. The switch circuits are required to use native growth nitrogen polar gallium nitride epitaxy process on a low-cost substrate. The primary expected transition target is transceiver applications for military and commercial systems operating in E and W band. For example, next-generation satellite communication links. Dual-use applications are expected to include commercial SATCOM, terrestrial backhaul, communications for 6G and higher, Wi-Fi 6, and next-generation wireless networks. During this Phase 2 project, a 2 to 18 gigahertz SPDT with 1 decibel compression higher than 10 watts and W-band SPDT will be developed on a low-cost substrate. Current state-of-the-art gallium nitride-based integrated circuit technologies are very expensive, with a significant portion of the cost coming from the use of small-diameter silicon carbide substrates. To enable large-scale production and adoption of microwave and millimeter wave MMIC systems, alternative, more affordable device technologies need to be developed. MaXentric Swing technology addresses this need by utilizing a cutting-edge nitrogen polar gallium nitride on sapphire process. This process uses low-cost, large-diameter sapphire substrates, which reduce gallium nitride MMIC fabrication costs by up to 6 times compared to conventional gallium nitride on silicon carbide processes. Swing also enables integration of a low-noise amplifier, a power amplifier, and a transmit/receive switch in a single epitaxial structure, which reduces transceiver integration costs by as much as 50%. Swing's key innovation is the combination of a high-performance, gallium nitride-based device technology with a scalable, low-cost fabrication process. Swing uses nitrogen polar gallium nitride high electron mobility transistors, which offer state of the art noise performance, power handling, efficiency, and linearity. These devices are fabricated on large diameter sapphire substrates, which significantly reduces fabrication costs. When combined, this enables cost-efficient integration of a high-performance low-noise amplifier, a power amplifier, and a transmit-receive switch on a single semiconductor chip for microwave and millimeter wave transceiver applications. The power and noise performance of these devices have been studied and reported, but more investigations are needed to evaluate the power handling and performance of the device as a switch. Two demonstrators explore the trade-offs between broad frequency bandwidth, low loss, high power handling in the 2 to 18 gigahertz and W band. Swing development is progressing as planned. During phase 1, transistor devices were modeled and characterized. Preliminary SPDT circuits were designed and launched into fabrication. The simulated performance meets the required specifications. During phase 2, which is currently ongoing, the phase 1 switch circuits were fabricated. Prototype testing is planned for summer 2025. A second iteration changing the metal mask is scheduled for tape out in fall 2025. A full redesign is planned in 2026 after evaluation of the second iteration. Swing is currently at TRL 3 and is expected to be at TRL 4, which is component validation in a lab environment at the end of phase 2. Swing development is fully funded by an STTR phase 2 base contract through September 2026. MaXentric has identified a suitable program of record, PE0602271N, Electromagnetic Systems Applied Research, as a potential transition path for phase 3 and beyond. This program contains a solid-state physics effort which explicitly aims to fund development and transition of N-polar GaN-based HEMT technology for advanced, highly linear receivers and efficient transmitters. MaXentric believes our swing technology would be an excellent fit for this program. Currently, phased arrays are one of the most expensive components in modern wireless infrastructure equipment. Lowering the cost of these components will enable wide-scale deployment of high-performing systems, providing real-time tactical data and information sharing between ships and aircraft. Compared to existing gallium nitride-based MMIC technologies, Swing offers higher performance in a more compact form factor at a lower cost. The use of a nitrogen polar gallium nitride device process offers lower noise, higher power density, and higher efficiency, enabling a reduction in size, weight, and power consumption of E-band transceivers. The use of large diameter sapphire substrates offers more cost-efficient MMIC production and scaling, enabling a 6x reduction in MMIC fabrication cost. Integration of low-noise amplifier, power amplifier, and transmit-receive switch on a single chip lowers cost and system footprint, enabling a 50% reduction in transceiver integration cost. MaXentric has identified several potential applications for our swing technology in both military and commercial markets. In the short term, MaXentric plans to focus its swing commercialization and transition efforts on the defense market, targeting high data rate wireless communication systems at W-band and electronic warfare systems at 2 to 18 gigahertz. SPDTs with low insertion loss and high power handling are required for high bandwidth directional and beamforming communications, such as distributed airborne reliable wide area interoperable network. Several prior and ongoing funding DoD efforts highlight the importance of capable mobile airborne links to improve and expand the tactical data link capabilities. Many of the electronic warfare systems operate in the 2 to 18 gigahertz band and would benefit from the higher power handling, higher efficiency, and lower swap provided by a MaXentric swing technology. The global electronic warfare market was valued at $16.65 billion in 2023 and is projected to grow from $18.32 billion to $36.67 billion by 2032, according to a report from Fortune Business Insights. The electronic warfare market size in the US is projected to grow significantly, reaching an estimated value of $11.41 billion by 2032, driven by rising aircraft refurbishment drive market size. Additionally, the following commercial market segments have been identified as potential applications for swing: short-range, high-speed wireless backhaul links, such as home networks and last-mile wireless broadband delivery, 5G, 6G radios, and SATCOM. MaXentric will invite interested parties, both military and commercial, to review swing prototype performance at the end of Phase 2. Based on partner and customer feedback, MaXentric will adapt the swing switch module specifications to satisfy requirements of the target application. Main potential clients include, but are not limited to, the Department of Defense and commercial telecommunications companies. If you are interested in MaXentric's swing technology, please do not hesitate to contact us. If you have technical questions, you can reach out to me at this email address or phone number. For business inquiries, please contact MaXentric's Managing Director, Human Gajari. Finally, if you are interested in our other products and technologies, please visit our website at www.maxcentric.com. This concludes the presentation of the Swing STP effort. Thank you very much for your time and attention. Have a great day.